Hi everyone, welcome to this supplementary video. In this video, we'll be focusing on cylindrical coordinates. As you saw in the last lecture, we have introduced cylindrical coordinate continuity equation, and we will be using that for the next couple of weeks as well. The sense I got was that not all students have seen cylindrical coordinates in as much detail, and there is some sort of confusion about what we are doing. So this video is mostly a basics, sort of will cover the basics of cylindrical coordinates. If you're not familiar, please do make sure to watch this video and sort of work through some of the calculations so that you're comfortable with the methodology. All right. So what is a cylindrical coordinate system? So basically, think of a 2D, two-dimensional plane. Okay. So we are talking about a plane, an XY plane. So think of like a sheet, essentially like a plane, which has an X component of Y direction. So if I have a point, which I am listing here as, let's say, X1, Y1, right? X1, Y1. Then we know that basically to reach to that point, we will go x1 in this direction and y1 in this direction. Sorry, x1 in this direction and then y1 in this vertical direction, right? So this is how you will sort of think about this. And if I want to denote that point, I will say it is x1 I hat plus y1 j hat, okay? So this is essentially how I will say this vector from origin to this one is x1 I hat plus y1 j hat. Hopefully this is clear. So basically first we went in x distance in this direction, and then we went into plus y1 j hat in the y direction. So this is sort of like a vector. Let's call this vector some a vector. Okay. So that's the vector I have from going from origin to that point. Now, that is one methodology, in which case we are using x and I hat and y1 and j hat. And so I want to clarify that this is a coordinate. This is a coordinate, right? This is a coordinate. And then this is a unit vector. Unit vector and a unit vector. All right, let me change this color. Right. Unit vector and a coordinate on sort of the two distinct components of this A vector. Now that this is my choice of using X and Y. And other approach is to change my unit vectors from I hat and j hat to e theta hat and er hat. So what we're saying is, instead of doing that, I will say, I will kind of argue that there is a way for you to think of it as er hat plus something e theta hat. Okay. So that's also it's also a possibility that I want to be able to do this. Okay. So the point now, what is this ER and E hat? So remember that I hat is this vector and J hat is this vector, horizontal and vertical. ER on the ER and E theta on the other hand are, this is a vector R ER hat, a unit vector. So a unit vector ER hat, and this is a E theta hat. Okay, so first thing to remember is this, that ER is radially outwards. This is radially outwards. Radially outwards. And E theta is perpendicular to this vector. Okay. So that's the first is a unit vector. However, unit vector is not the only part of this. I also need to be able to understand the radial and the coordinates essentially. So x and y are coordinate, x1, y1 are coordinates, and I and j are unit vectors. So I have er hat and e theta hat as unit vectors. Now I can also define coordinate system. So remember, we will say this is an angle theta. So maybe let's just do with the same example of x1 and y1. Okay. So now x1 and y1, I'll say r is this distance from the origin. So we'll say r is this distance from the origin. So in this case, it is x1 square plus y1 square. And theta is the angle with the x-axis. Okay, so theta is the angle with the x-axis, or you can say it is cos of theta equal to x1 by r. So remember, if I draw a triangle here, then this distance is x1. So cos of theta is x1 by r. You can say tan of theta is x1 by y1, or you can choose any of these options. So r is now the distance from origin. A common mistake is sometimes students think of r can be negative, but it is always positive. Okay, and theta is the angle, with x-axis. Okay, with x-axis. So now that also helps you probably visualize that er is radially outwards, as I've pointed out here. Okay, and e theta is perpendicular to that, because when I'm going from theta will kind of go from here to and so on. So some notes here that r is greater than equal to 0, and theta is always between 0 to 2 pi. Okay, I can basically complete a full circle by going with theta from 0 to 2 pi. I can complete a full circle, and that will be able to cover all the points on that plane. So we can, instead of using x and y, I can use r hat and theta r and theta to define my points. And similarly, I can also use this to define er hat, and e theta hat. So there are two different parts of this. Okay, remember, this is the most common confusion I've seen. I will emphasize that there is a coordinate point, which is r and theta, which is just a scalar value. And then there is a vector part to it, which is the er hat and e theta hat. Okay. So what is this er hat and e theta hat? Remember, I have sketched it like this, and you have seen it now. This is theta. Okay. And e theta hat is vertical to this, so normal to this. So remember, I have said if a vector makes an angle theta with the horizontal, is perpendicular will make angle theta with the vertical, right? This angle will be also theta. And essentially what you can see is er hat is equal to cos theta I hat plus sin theta j hat. Okay. And then I have e theta hat is equal to minus sin theta I hat plus cos theta j hat. Okay. So if I take the components of e theta, I'll get cos in the vertical, right? This is hugging the vertical direction. It's the cos. This is hugging the I hat direction. So it's the cos theta with the I hat. And the negative sign with minus sin theta is because ER is pointing towards left, right? If I take the component. So this is another way to think about it. So now note that ER hat and E theta hat, I am allowed to keep this cos theta, sin theta here. All I'm doing is I'm just decomposing that into I hat and J hat. Cos theta, sin theta are simply values. These are just, some sort of numbers. But when I say ER hat, I'm really meaning cos theta I hat plus sin theta J hat. When I'm saying E theta hat, it is sin theta I hat. So I have two directions within that ER hat. Okay. So essentially, this is the way we think of radial coordinate system. And in the next video that I'll show you an example to further illustrate what is going on. But now let's go back to and just to give you practice. I have an A hat in X1 I hat plus Y1 J hat. That is what I've been given. Now, how do I present that into ER hat and E theta hat? Okay. So I will call this number here AR, and I want to find AR and E theta. So I've been asked to find AR and find A theta. Okay, you've been given that this X1 and Y1 are this. So you've been asked to find what are the values of AR and A theta. Okay. So this is a vector A, which goes from origin to point X1, Y1, which we have discussed in Cartesian coordinate. Hopefully that is clear. Now I've been asked to find what is the value of AR and A theta. So now let's do that. What I really need to do is I need to decompose, because I want to compare these values. I want to compare these values. So I should decompose my values into I hat and J hat. So now A vector, is equal to AR ER hat plus A theta E theta hat. Okay. Now this is equal to also equal to X1 I hat plus Y1 J hat. Okay. This has been given to us. Now I want to be able to compare. So I will say AR, I'll convert it, I'll put these values cos theta I hat plus sine theta J hat. Okay, plus A theta into minus sine theta I hat plus cos theta J hat. Okay, is equal to X1 I hat plus Y1 J hat. All right, so this is what I have. I have the full point, expanded the ER hat and E theta hat. Now I can compare anytime I have a vector equation, I can compare all the left-hand side of I hat and all the left-hand side on the left-hand side of J hat. What do I mean by that? So A vector is essentially equal to AR cos theta minus A theta sine theta. I hat is plus AR sine theta plus A theta cos theta. J hat is equal to X1 I hat plus Y1 J hat. Now, this is still a vector equation, but now I've separated everything. I've combined sort of these two terms with I hat and these two terms with J hat. I can now start to compare, right? So I can compare what I can say is AR cos theta, AR cos theta minus A theta sine theta equal to X1 AR sine theta plus A theta cos theta plus A theta cos theta is equal to Y1. Okay. So I have this, clearly I have this value, and we should not forget that this is what we have, but we also know that cos theta is equal to x1 by r, and so we have those descriptions varying. So the reason I want to separate this is, remember that this ER hat is a vector decomposition, but we also have these scalar relationships of cos theta x1 by r and so on. But we will come to that in a second. Okay, so we get this value. Now I want to find the value of AR and A theta. I already know the value of cos theta sine theta, by the way, but we want to find the value of AR, A theta, AR, and A theta essentially. So I can see clearly if I multiply this by cos theta, multiply by cos theta, and multiply this by sine theta, right? Then I will get AR cos square theta and minus A theta sine theta cos theta, and then I can add them, right? So what I'm saying here is I can say AR cos square theta minus A theta sine theta cos theta is equal to x1 cos theta, and AR sine square theta plus A theta sine theta cos theta is equal to y1 sine theta. Now if I add them, if you add them, then we get AR. So this will go away, the A theta part. So I'll get AR cos square theta plus sine square theta is equal to x1 cos theta plus y1 sine theta. Okay. And finally, this means that AR is equal to x1 cos theta plus y1 sine theta. But we are not done. We do know the value of cos theta and sine theta. So remember that cos theta was x1 by r, and then you can confirm very easily that sine theta means y1 by r. Okay, because you know that is the opposite on this triangle from where we had find it. This is y1, right? So we can say this is x1 into x1 by r plus y1 into y1 by r, and this becomes x1 square plus y1 square by r, or r square by r, or this is r. So my AR is equal to capital R. Okay. So now my answer essentially becomes AR is equal to capital R. Finally, we can use this to put this back in this equation. So this will become AR is equal to R, substitute back, substitute. So this becomes R cos theta minus A theta sine theta is equal to X1, right? And remember again, cos theta is X1 by R. So this really is X1. This goes away, and so you get A theta is equal to 0. A theta is equal to 0. But finally, what I'm getting is A vector is equal to AR hat. And there is no A theta because A theta is 0, or simply this is R hat. And this is also equal to X1 I hat plus Y1 J hat. Okay. So what was the point of doing all this analysis? So essentially what we are saying here, and this also makes sense now once you see this, you can't unsee it. If I have a point X1, Y1 here, I can also say I have gone in just radially outwards with a distance of R, and there is no angular dependence of E theta, right? I'm just going from 0 to that vector. So it's a radially outward vector. So there is no angular E theta hat dependence. It's simply just a distance multiplied by the vector which goes radially outwards. So basically any vector that is going from origin to any other point is simply RER hat. So this is a compact way to write. Instead of writing like this, you can write simply like ER hat. So this sort of helps you see how these two kind of coordinate systems are comparable. So the whole idea behind a cylindrical coordinate system really is that you are writing an X and Y in terms of R and theta. R is the distance from the origin, and theta is the angle of the X axis. On top of that, you also have, this is the coordinate choice. And then you also have a unit vector choice, which is ER hat and E theta hat. And ER hat is something which is radially outwards from, radially outward direction. And E theta is perpendicular to that direction. And so they are related to I hat and J hat using a theta. So, and theta depends on, again, the X1 by R and local coordinates. So the whole point is that instead of going like, horizontal and a vertical direction, I am kind of going around in a circle. I'm going in a sort of a circle where I have a distance and an angle that I choose. And as you will see, this is important because if you're using pipe flows or you have some other cylindrical systems, this coordinate system helps you. Okay. So in the next video, what I'll do is I'll give you another example of a system where something is given in cylindrical coordinates, and then I'll convert that into Cartesian coordinates and show you how everything is self-consistent. Okay, so hopefully this video kind of gave you an idea of what a cylindrical coordinate system is, and the idea being using this R and theta dependence. And with that, I'll close this video and look forward to seeing you in the next video.